Kellens from the DOE, Brussels, Belgium. So, good luck.
Thank you. So, good morning. Today I will talk about one of the tools that we developed at our lab, which is called the Intentional Views Environment, or the cute name we give it is IntensiVE. So the idea of this tool is to allow developers to do some kind of agile architectural conformance checking. Now, to start, let me explain a bit what we mean with this. So if you take a look at architecture and design of software, well, okay, it's always very nice that people make a nice design, a nice architectural description of their software. However, people also try to encode this somehow in the actual source code of the system. And well, how do we think that people do this and how we observe this is that they use what we call regularities, which are the patterns, the underlying idioms, all the stuff that people use to just say, okay, this concept in my design is now reflected as such in my implementation. So examples of these things are the simple stuff like naming and coding conventions, the idioms that you use, particular protocols, the way that you actually implement design patterns, how your modules in your system are interacting, best practices, anti-patterns, bad smells, all of these kind of things. Now, if you take a look at how these regularities are actually documented, well, people use something which is quite informal to do this. For instance, they use architectural description languages, UML, English, or probably here Spanish. But it's something that's so, well, it's very informal. It's something that's not really linked to the implementation itself. So, well, as a result, you end up with a nice design. You do the implementation, and well, over time you're wondering, okay, all these rules that we have specified, are they actually adhered to in the implementation itself? While this may not be a problem when you start with the implementation of your system, of course, over time your software starts to evolve. You get new versions in your software, you can get basically a mess, and you have no idea anymore, is my system still adhering to the actual documentation, to the different naming conventions, implementation idioms, and so on. Of course, this then becomes a problem because it makes your software more difficult to understand and hence to maintain. Now, the idea of IntensiVE is just, well, to offer you a tool where you can actually specify and that's a bit too fast. Okay. Where you can actually specify these design rules, these regularities using our tool, and where you can verify their validity with respect to the actual implementation. So what we have is a tool suite where developers have a number of subtools to write down this kind of documentation, and I'll show you how in a couple of minutes. And to verify, well, okay, do these rules, do I adhere correctly to these in my implementation, and even to visualize them, and so on. Okay, so my presentation actually consists of two parts. I'll first explain a little bit the concepts underlying IntensiVE, and then I'll take a look at a live demo of the tool where I'll just show you how we can document something. So I like design patterns as a kind of a way to explain these kind of things. So I hope everybody here is a little bit familiar with the gang of 4 design patterns. First, this is something quite universal. It's not that the tool can only do design patterns, but just this is something that's very easy to explain. And there's lots of different rules you need to adhere to, and well, they make it easy to explain our tool. So the one I'll use to explain the concept of the tool is the abstract factory. So just to remind you, the idea of an abstract factory is that you can have, well, different families of products that you want to use in your application, and you want to use them interchangeably. And then a factory allows you to actually extract the object instantiation from the implementation, and by putting in a different factory, you can use a different family of objects. So I'll take a look at one particular example of a factory, which actually comes from an industrial case study we did. So it's not that I'm lying, but this is just a small example. Just something that we observed in one case study with a medical company. So what they have is actually they have a whole event system in their implementation, and they have different kinds of families of events. They have, so right here, yes. So they have, normally they have default events and they have lenient events. So I'm not sure anymore what they really meant by this, but it's just to indicate we have 2 kinds of events. Now each family of events is just defined by 3 events, namely an error, a notification, and a request. And then of course you see that we have an abstract factory which just says, okay, I define a method to create a request, a method to create an error, and a method to create a notification. And then we have we have 2 default factories, two concrete factories, the default event factory, which creates the default events, and a lenient event factory, which will create actually your lenient events. Now, if we take a look at this instantiation of a factory, we can see that there's actually quite a lot of regularities that developers need to adhere to. A very almost trivial one is that, well, all my concrete factories, they must be actually a subclass of the abstract inventory class. If not, well, they're not a factory. Similarly, there's a very simple naming convention which says, well, all my concrete event factories, they must be suffixed with event factory. Remember the names I called them: default event factory, lenient event factory. If you make a subclass of your abstract event factory that's not really called an event factory, well, it wouldn't make sense. A more interesting regularity is that any kind of product that is instantiated in your application should be created in the factory. This is a really important one, and actually it's the most important one you need to adhere to when using the factory. If not, it can happen that you're creating events in your code, and well, you change the different factories. If you have places where the event factory is not used, well, then you can have you can use events from two different families of events, and just believe me, in their system this would be really, really bad. And the final one is that, well, okay, your factories must be complete. Each of your factories that you define must have a factory method that creates an instance of each of the different kinds of abstract products that is defined in your instantiation of a factory. Okay, so let's actually take a look at the first two kind of regularities. So the fact that each factory should be in the abstract event factory hierarchy, and that they should be suffixed with event factory. Now, the whole idea behind IntensiVE is that you can always, you can group interesting concepts in your code by such kind of definitions. So what we can say is actually these two kinds of regularities, they turn the concept of what is an abstract factory, which is something quite implicit in your code, they actually turn it into something very explicit. If I need to talk to one of the other developers of the system, I can say, okay, the guy asks where are my factories? Well, I can say, okay, take a look in the abstract factory, actually the event factory hierarchy, or okay, take a look at all the classes that are actually called a factory. Now, based on this observation, what we do is, well, we define something which we call an intentional view, which is nothing more than a set of source code entities. So, for instance, I can define a set here which I call all subclasses of abstract event factory. We would call this an intentional view, and well, it's just a specification, something intentional, and well, this characterizes what is an abstract event factory. Similarly, we can say, well, I can also characterize this kind of concept by saying all the classes that are named star event factory, so that are suffixed with event factory. And then, of course, well, the idea behind IntensiVE is that we can specify constraints over these sets of related source code entities. For example, the first kind of constraint is that we can say, okay, actually, in a perfect system where my factory is implemented correctly, these two sets of entities should actually be the same. All my classes that are implemented in the abstract event factory hierarchy should also be named event factory and the other way around. So what we can say is this is a kind of, we call this alternative intentions, alternative descriptions for one set. And ideally, if you start looking at this kind of documentation, all my actual event factories should be in the intersection of both sets. If I have an if I have a subclass of abstract event factory that is only in this set, but it's not following the naming convention, well, I have a violation. The other way around, if I have something that is called event factory, but it's actually not in the hierarchy of my event factories, I have another violation. Okay, now the third kind of regularity, namely that all my products should be created throughout created through a factory. We can also document this as a sort of alternative specification of a set of abstract factories. If you would think of this more in an imperative style, you could say, how would I calculate this set of violations? So I would say, okay, first I need to specify which are my products. Okay, I have those. Then I would need to specify which are my classes that are implementing the factories. I need to find all the locations in the code where my where my events are instantiated. And then I need to mark all the locations that are actually not inside of a factory. Well, what this actually boils down to is that we can just say, okay, just another way of specifying what do we consider an event factory. Namely, all the classes that are actually instantiating events, well, those are event factories. So we have now already three definitions of the same concept, and this is the whole idea behind the tool is that, well, you can specify a set of entities and constraints between these entities. So again, if we look then, ideally all my event factories are in the intersection of the three definitions. If I now have some class that is actually instantiating events, but it's not in the correct hierarchy, or it's not following the naming convention, then we have a violation of the design pattern. Then something that I shouldn't forget to mention, something that we'll see later in the tool is actually, these sets of these intentional views, they define a concept in your code, but the nice thing is that you can also define these concepts in terms of each other. So when we have here this description which says all classes that instantiate events, well, again, events can then again be a definition with a whole different set of its own intentions which specify the set. Okay, so this is basically the idea behind the tool, namely you have something which we call intentional views. An intentional view is just a set of source code entities that are conceptually belonging together, and that instead of being enumerated, so instead of saying this event factory, that one, that one, that one, is actually computed. So instead of being manually enumerated. I'll go later into details about how you can actually write these intentions, how you can actually write these sort of queries that compute a set of source code entities. And then of course, we verify conformance of the documented regularity by just taking a look with this kind of example, which are the entities that are not in the intersection of all my definitions, and we consider those as violations. So this is a screenshot of the tool that we can use to document these kinds of alternatives. So later on I'll show you the tool concretely in a demo, but for now I can just say it's implemented in Visualworks. And okay, what can we see here? So we see actually that the tool allows us to create something, the intentional view. Here we call it the common event factory, but this is my abstract event factory view. And we can give multiple definitions, each by specifying a separate tab where we give the definition of the view itself. Now the more interesting thing is that we can actually then check the validity of this view with respect to the implementation. And we get a tool which starts reporting on violations. So in this example, for instance, you can see that, well, we have 8 classes which are actually adhering to any one of the definitions, but there are a couple which are indicated, quite a lot actually, 6 out of 8, as a violation. So what we see is that for each class that was identified by any of the queries, it starts indicating in each of the columns which align with, so this one is based on the subtype hierarchy, this one based on the naming convention, and that based on the fact of whether the class creates events. It will indicate with a green dot if it's correct, and with a red mark if it's a violation. So what we see here is, for instance, we have here a class called the properties changed serializer, which is actually creating events, but it's not in the hierarchy of my abstract factory, and it's also not following the naming convention, so clearly we have something that went wrong in the implementation. So actually one of the interesting things that we could show to this company, well, while they have a very simple factory design pattern, they already violated it with a small part of their system. Okay, so another kind of constraint that we can specify are not really multiple definitions of one singular concept, but actually relations in between of different intentional views. So to illustrate this one, let's take a look at the fourth regularity, which specifies that all my factories must be complete. So what this boils down to is that we have one intentional view, which groups all the factories I have in my system. Another intentional view, which groups all my event types, so all my abstract events. And then in an ideal situation, for all my factories, it should be true that they create event types of all abstract types. Of course, they have to identify them, so they must be complete. Anything that does not adhere to this relation is then a violation of the fact that the factory is not complete. If it does, then everything is okay. Okay, so yet again we have a tool where you can specify this, but I'll go into details later about it, just to show that yet again you can verify this. We have some visualizations which allow you to see, okay, for all my factories, well, I have here one particular factory which does not create these 6 products because, okay, we indicate the violations in red. Okay, so this is basically what the entire tool suite boils down to. It will get more concrete when I get to the actual demo, hopefully. But before doing that, I want to discuss a little bit about the query language that we use to specify now these queries. So in my slides before this one, well, each time I was defining a set as well all subclasses of abstract event factory or all classes which create an instance of an event. Well, this is just natural language. Now, of course, in Smalltalk you can do this by just using the meta-object protocol. You could just say abstract event factory, all subclasses. Okay, this works actually fairly well for quite simple examples. If you go into more complex queries that you want to ask, well, we found something that's a bit more elegant to express these kind of things, namely the use of a logic language which we call SOL. So the idea of SOL, which stands for the Smalltalk Open Unification Language, is as a Prolog implementation on top of Smalltalk that's specifically tailored towards reasoning about the structure of programs. So that actually you can do structural reflection, not by using the Smalltalk meta-object protocol, but by using regular sort of kind of Prolog queries. Unique to this language is actually the fact that it's not a pure logic language. It's a hybrid language in which you can use Smalltalk blocks and Smalltalk terms as objects in your logic programs or even as logic conditions. Okay, so to illustrate a little bit of how the language looks like, I have a very small system here. You don't even need to read what the different classes are. It's just, well, the idea that you have a system with a number of classes. What I can do with SOL is I can say, okay, I can start querying my system. So I can ask it to query if $X is class. Now, for the people here who knows Prolog, this already is a little bit different from what you're used to. First of all, instead of using capital letters for indicating logic variables, we use question mark. And the second thing is that instead of using the typical predicate notation where you have your predicate name, open parenthesis, your arguments, close parenthesis, we kind of use a Smalltalk messaging sort of syntax. So we can just say if something is a class. Now the cool thing is then, of course, you can type in this query in the interface and it will just start evaluating and it will hand you all the classes that are present in your system. Of course, this is still a very, very simple query. I'll show you a couple more complex ones later. Okay. Now the nice thing about Prolog is that, well, your predicates are bidirectional. So I have a predicate here which says the isClass predicate. I can not only use this to query whether something is a class, I can also use it to say, okay, for this particular entity, this particular object, are you a class? So I can specify, okay, the Smalltalk block node, this evaluates to the class node, and I can just say, okay, is this a class? And in this case, it will then yield true. So what we have in SOL is actually a library of predicates that allows you to do reification of all of your the entities you have in a Smalltalk program, so classes, methods, and so on. Of course, you can also query the relationships between these entities. For instance, we have one predicate that is superclass of predicate, where you can just say, okay, if some logic variable super is a superclass of some other class, which we call a subclass, and you can even write predicates which are actually deduced. So it's not only limited to reasoning about the actual structure of your system, you can also extract more information like deduced relationships, such as, well, some class, is it above another class in my inheritance hierarchy? Okay, so then, okay, you can query it again and we'll get all the nice pairs of super and subclasses. Okay. One of the interesting features about SOL is that, well, because it is implemented in Smalltalk and because there you have access to your actual code as an object tree, well, we can use this. So something, if you're a bit familiar with how source code analysis tools work, well, one of the typical things people have to do there is to write fact extractors. Some piece of software that will just take a piece of your source code, that will manipulate it in some format which your tool can then work with. Well, one of the neat things is that we don't have to do this, simply because we have Smalltalk. Our language is implemented on top of the Smalltalk environment, and we can use the Smalltalk objects. Well, we can just reason directly over the actual objects representing the classes, the methods, and the AST nodes. So just to show you this, you can just, if I query so if I query all my superclass relationships, I can just click on one result, double click it, and I will go to the actual definition in the Smalltalk browser. In my demo I will show you a little bit more complex example. So to give you a bit more of a feeling how the language works, let's take a look at how we would write down a query to detect the composite design pattern. So yeah, I really like design patterns for these kinds of things. So the composite design pattern is actually very, very trivial one. It's just, well, the way you can make a composite object. Yeah, for instance, a parse tree structure is something which you typically would use a composite design pattern. How this pattern works is that you actually have one abstract class which you call your component, and it has two subclasses, your leaves and your composites. And the idea is that, well, your composite will then contain a set of components which are the children of your composite. Now, okay, so the query to detect this design pattern is actually, okay, I spread it out over multiple rules, but it boils actually down to finding the structure of your design pattern and the actual aggregation that is used inside. So my predicate that I defined here is so I have some particular question mark components or particular logic variable component is the root class of a composite with a composite that uses a particular message. So something that's also very typical to the composite design pattern is that operations on the composite are actually implemented by iterating over all the children and just sending the same message to those children again. To detect this rule, I have two simple logic clauses. I first will say, okay, I'm looking for the composite structure, and then I will look for the aggregation that actually does all the delegation of the message towards the children that are part of my composite. Okay, so the structure is actually something very, very simple. It's simply, the only thing we can say about the structure of the composite design pattern is that there is an inheritance link between your composite and your actual component, and this is exactly what this query expresses. You say, okay, my component should be a class, and the composite should be a subclass of the component. Of course, this does not truly characterize the actual implementation of the composite. It's only when you combine this together with the aggregation query that you'll actually start finding all instances of the design pattern. Also, you're just querying subclass relationships between two nodes. Okay, how does the aggregation work? Well, this is a little bit more complex. We just say, okay, my component implements a particular message. So, okay, my component, the operation. I'm looking for a method with the same name that is implemented in the composite. So I will find this one. Then I will query all the statements that are present in this method, this one, and I check whether there is an iteration block in that method that actually iterates with the message, which is the message that's shared between your component and your operation. Now we can let this run over the entire VisualWorks image, and it will return 81 solutions over almost 8,000 classes in something like 13 minutes. So this is something where I should warn you about. Sol is about 30 times slower than you take a look, for instance, SWI Prolog or some other commercial implementations. Now this is a bit of a lie because, well, this slide is actually 2 or 3 years old. We have been working on optimizing the language using table Prolog and things like this, but still it's a couple of factors slower than a regular commercial Prolog. However, yeah, you get the neat features that you can actually use smalltalk terms in language itself, which, okay, I'll not go into details, but just believe me, it's a very cool language feature when you're writing software engineering tools. Okay, so actually now the main part that I wanted to come to is a demo of the tool. So I'll also try to speak up without using the microphone, because I also have to type.
You can use the microphone instead, yeah. Just...
Oh, that's heavy. Okay. So, no, I'll just do it without the microphone. It will be easier. So what I have opened here is actually the IntensiVE tool suite. So for the people working with VisualWorks, you might know the star browser tool. So it's something that was written quite a long time ago. It's a classification tool done by Rulebox. And actually IntensiVE is implemented as one subpart of this tool. Okay, so what I have opened here is the star browser with the IntensiVE extensions loaded. So what you see here is that we have we have one tree node which we call intentional, which is just the root node of the system. And underneath we can start defining projects which contain the views and the relationships that you define over your own software. So I made a special one which we called smalltalks to do the demo here. And I'll document now, a little part of a visitor design pattern that is present in the implementation of Star Browser itself. So what you can see in Star Browser, you have to now decouple from the fact that this is also the tool, but what you have here is just a tree structure. You have your different nodes, and you have composite nodes, and you have leaf nodes which do not have any children. Well, in the Star Browser, all the operations over this tree that you see here are implemented by means of a visitor pattern. So the idea is that you have something which is called a service, and in order to display the label that you can see here, or the icon that's in front, or to display the editor you see on the right, there is each time a separate visitor that actually specifies the behavior for each kind of node that you have in here. So maybe it's easier even to show you. So what we have here is we have the service class, which is the root class of my visitor design pattern. And as you can already see, it implements quite a lot of operations for a bundle model, class, classification, and quite a lot of other things. Now, for instance, let's go to one of the elements that are visited by this visitor, and those are classifications. Well, you can see that each classification, so these are all the objects that are in your object tree, they have to implement an accept method. Well, this accept method will just take a service. Okay. So what you see is they implement accept service. Accept service is a method that follows actually quite well-known idiomatic implementation, namely that of a double dispatch. So accept service has one single argument, the actual service that it accepts. And what it will do is it will say, okay, I'm sending to this argument that I received to the service a message that is, specific for my own implementation. So for classification, it's do classification with myself as an argument. So this is a typical double dispatch protocol, something that's fairly well known, and that's really something typical to the visitor design pattern. Now let's try to document this using IntensiVE. So let me take the tool back. So what we can do actually in IntensiVE is, I can create my intentional views similar to the one that I've shown you before, concept. Something is a little bit more, interesting about these definitions is that, we also structure them as a kind of a tree where you can refine the queries that define them. So for instance, to, take a look at which are my accept methods, I would first actually create a view which groups all the classes that are part of the structure, the object structure that is visited by my visitor. Now how I define this one is very simple. I just say, all the classes that are in the hierarchy of, the namespace classifications so to get the class abstract classification, I consider these as the objects in my structure on which we have defined the visitor. Now, something you can also do with IntensiVE, and I can even show you here. So here I have used Sol as the query language, but because this is a Smalltalk community, I can now actually even say, I can show it. It doesn't need to be a Sol query. You can also just use a Smalltalk block that will create, the view that will gather all the elements. It's a little bit more verbose to do so. So that's why we actually prefer Sol, where you can do very complicated and very quite elegant queries in a single or a couple of lines. So what we see is, so we have class is a class in the hierarchy of abstract classification. Now to also define the view, I need to say which are actually the elements from the query that I want to see in the view. Because your query, it can contain quite a lot of conditions with lots of logic variables, but actually, your view should contain tuples containing only the elements you're interested in. So for this one, I only said, I'm only interested in actually only the single variable we have here, namely the class variable. So if I now ask to compute, it will just give me the list of all my elements in the structure that we have a visitor defined over, and you can click on one, you can browse it. Yes, it even work. Does it work? Nope. I just played around with 7.7.1 since a couple of days, so probably there's still some bugs in there. So this is not the interesting thing. Now, how would we take a look at the accept methods? Well, accept methods are actually methods that are defined on the object structure, and that are the accept methods of the visitor instance. Now we can specify these accept methods in two ways. So something that I should have shown you, if we take a look at accept service, that's typed wrong. I followed a particular kind of convention that I put all my accept methods in a protocol called operations. So this is a nice way of characterizing the concept of my accept methods, namely all the methods that are classified in the protocol operations on a class in the hierarchy of my abstract classification. So let's go back to this one. And we can exactly specify this query using the install. So for instance, we can say here, okay, I'm interested in all the methods in a particular class. Mind that this view is defined as a sub view of structure. So class already will be bound here to all my my elements in the structure, all my abstract classifications. And we say, okay, this method should be classified in the protocol operations. Now, another way of specifying the same view is by name. Namely, this is a fairly trivial one. All my accept methods should be called accept service. If they are not, well, they are not an accept method. So we can do this the same way. We can just say method with a name in class, and the method accept service and class. And then I can ask the tool to verify the validity of this view, and it will immediately report me on all the inconsistencies. So there are actually, in this case, because the implementation is fairly clean, there are more consistencies than inconsistencies. But if we take a look, we see that, for instance, we have one method here on IV extensional view, which is called accept service. So it is part of the second alternative. The name is correct, but apparently it is not classified correctly in the correct protocol. Other ones are something which is called root view check with bindings and copy, which apparently are put in the operations protocol, although they are not accept methods. Well, this is now a fairly simple. Actually, I shouldn't be showing this because this is my own code that's wrong. So I'll just blame it on the student who wrote the extension. Okay. Now, this is a very simple convention. It's just a naming convention, and it's just, well, a protocol convention. But then again, these are the kind of things that make your software really easy to read and really easy to understand. It's a kind of, well, the idea that you can enforce the different kind of patterns that you have in your code, and that you can actually make sure that people obey your conventions and your design principles. Okay, but this is actually the fairly trivial one. Now, we can do the same trick for the visit method. So believe me, you can define it in the same way. It's actually literally the same way, saying all the methods which are named do star and that are also classified in the operations protocol. But this is not the interesting one. The interesting one is the double dispatch itself. So we want to make sure that all my accept methods actually are implemented using the double dispatch protocol itself. So how we do this is we create what we call the intentional relation, you can see here on the screen. And we say, okay, for all, and you can choose actually some other quantifiers too. I can say most, some, not exists, exists only one, and so on. But this one I say, okay, for all accept methods, it should be true that there exists a visit method, and we can specify some aliases for the elements in the views. So the accept method we call accept, the visit method we call visit, such that the following logic predicate, the following logic program needs to be true. Now remember from the pattern that I showed you before, well, I was expecting my accept methods to be implemented as a single statement. So this is what the first condition expresses here. So, okay, for the people knowing Prolog, in Prolog you indicate lists by means of the square brackets, but in Smalltalk they had already some use, so we just opted to use the fish brackets, the smaller and greater than sign, to indicate list. So what we can say is, okay, all my statements of my method, I will query those, and I will say this should be a list with a single element called statement. And I can actually say, so here I can say my accept.method is the way to get to the value of the binding of the method variable in your accept method. We do the same thing for the arguments. We say, okay, my accept method should have a single argument, which we call argument. And then we extract the name of the message from the visit method. So if your visit method is do classification, well, message will be bound to actually the symbol do classification, the name of the method, selector. And then the neat trick is that we can say, okay, in the syntax tree of my statement, I should have one particular node, an RB message node, where the receiver of my message is the argument, so the first argument of the accept method. The message that is sent is the message implemented by the visit method, and the arguments of my call to the visit method should be a single argument, namely the RB variable node self. So for people...
Sorry to interrupt you, but I didn't understand why you are using a relation. What's that in the top? Whether it says relation, and why don't you use Sol to write all that, like in the other example?
Well, Sol is a logic language. Okay, the idea would be you could do it with the logic language, but you could write a predicate for all, and you could write a predicate exists. Actually, that's how this is implemented.
Okay.
But there are some more tricks underneath the hood. Since the analysis itself, well, this would lead to quite a big combinatorial explosion. Because in the first versions we did it like this. You just wrote it down with the query. But we opted not to do it anymore simply because you can do quite a lot of optimization in the checking if you can say, okay, I do lazy evaluation of my for all. If I find, it has to do with some optimizations. Also because we have a couple of people now working on extensions of the tool that, for instance, automatic fault correction. And then it's easier to use this kind of description where this is actually the for all and the exists quantification is part of the framework on top of the logic language and not of the language itself. There's also a very pragmatic reason. If you say for all, is this true? It will just say true or false. It will not even report you on the inconsistencies. So you would have to do some tricks there anyway. So it would make it also a bit more elaborate to write down. So we can just write down the double dispatch like this, and I can show you that it even works. It does the check. And it will say in this case that, well, its verification succeeded. So it's true that all my visit methods are all my exit methods are following the double dispatch protocol. Now, so, because I see that I'm almost running over time, the last thing I want to show you is that, well, remember the title of the presentation was Agile Conformance Checking? Well, this is not very agile, the tool I have shown you. Simply, it's a separate tool. Now, the idea is actually that you can use these kinds of tools similar to how you use unit tests. So in your unit test, you would check your behavior, you would write down what you expect the program to do. Well, with this kind of tool, you can write down how you expect the program to be structured. And we simply can also, so let me check this. We can also just run this as a unit test. So it integrates with the unit test framework. I can just run. It will say, okay, I have one regularity because I didn't show you the entirety of the tool. We have means to group together views and relations into what we call regularities. I have one regularity that failed. If I click on debug, it will then show me the tool illustrating the exact part of the regularity that was documented that was not adhered to, and this would be the silly naming convention that I had and I've shown you a couple of minutes ago. Okay. So to conclude, so we have actually, well, the tool originally was developed in VisualWorks, so it's a quite mature version of the tool. We've been working on this tool for something like 5 years. The logic language itself is actually quite old. It started in 1996 by Roel Wuits, who most people in the Smalltalk community are familiar with. I also want to mention that we don't use it only to reason about Smalltalk, because, well, as an academic, well, you get, and if you want to do a couple of industrial case studies, well, you're bound to get in contact with Java and other horrible languages in any case. So we have a version of the tool that reasons about Java code, but also from within Smalltalk. So it's something that Johan Brichot demonstrated at a couple of ESUGs ago. It's with Java Connect, and actually it's kind of pervert because we connect via Smalltalk, we connect with a running Eclipse instance to get the parse trees, but yeah, you don't want to know about this. We have the same kind of trick to reason about C++ and C, and I even did a version to reason about COBOL because, well, we had to. So the tool itself is tightly integrated with the IDE, with Star Browser. You can directly browse the code from within the tool, and, well, you can play around with it. We try to make it as easy to work with as possible. If you're interested, we have a website where you can just download the instructions, how you need to install it. I'm also working on a version for Pharo and for Squeak. So what we have there is that the logic language runs without a problem. The model itself and so of the intentional views that works also without a problem, but, well, we don't have user interface yet. I have a simple web interface written in C-side, but that's not nearly as finished as we have with the VisualWorks interface. But if you want to try out, or even if you would like to write an interface for this, everything can be downloaded from Squeak source. Okay, so that's basically the end of my talk.
So if you have to analyze the parse tree of the method in your tool you have, I guess, to analyze or visit the parse tree of the method to gather information.
Yeah. Well, actually, it's good that you ask. It's a very interesting question. The fact is that we used to do this with just regular parse tree reversal, but then we found a neater way because, well, this small talk, you have your objects, and if you know a little bit about Prolog, well, the big underlying concept there is unification. That you have, well, you can unify values, you can unify structures with each other. How it now works is that the parse tree traversal, we kicked that one completely out, and it works by, well, a sort of implicit traversal where we defined unification on the actual RB, or the refactory browser syntax node. So when you're writing down stuff like RB message node, it will not really do the traversal, but just really try to unify this with each of the nodes in the actual implementation. So it's fairly well integrated with language.
Have you found that using this unit for results is perhaps a little bit cumbersome because in this unit you just get errors, failures, and access and nothing else?
Yeah, the only thing where it really makes sense is that, well, okay, you can. It's easy because, okay. Well, the integration with SUnit is indeed very trivial. So the only thing that we really support is you can just run the verification of the documentation and the debugging that works really well. But of course, yeah, running everything again, and that's not really that well integrated. So it's indeed maybe a little bit cumbersome to do this kind of integration. But on the other hand, it makes it easy to just say, okay, each time that I change something in implementation, I will run my unit tests, and I will just run all the structural tests too. So I haven't showed it here, but I actually documented the implementation of the tool itself, using the tool itself, a kind of eat your own dog food experiment. And it's fairly fast to do this, so I can verify quite a lot of things in something like 15 to 20 seconds. And I found that sometimes it can be quite interesting that you make some changes and you immediately find stuff where you were a little bit lazy or a little bit sloppy. And in this regard, I think the SUnit integration can be useful.
Andy, I guess that lots of this is post-hoc, in that you're coming up to analyze existing designs. But I wonder what the system would look like if it was pre-hoc, if this was more of a high-level design system.
So,
in that, one can express designs by writing these predicates in the first place.
you would use it as a kind of design up front ways, like test-driven development that you would use for view-driven development. Yeah, that's very interesting, because it would be an interesting methodology to try out, but of course, we haven't done this, because even with the projects we're doing now, it's more of a kind of a posteriori way of working with it. Because same way, actually, I don't think we're very good developers, because the same we do test-driven development, namely we write unit tests, but we always write them afterwards. It would be interesting for one of the new projects to just try to start with also defining the views. But then again, I don't know whether this would really fit in that well with an agile development methodology where your design changes quite rapidly. So each time this would probably indicate more of an effort, because each time you'd also need to change the documentation when you start refactoring the system. It might actually be interesting for some research that the system could become refactory aware, that would maybe do these things.
Refactor the design.
Yeah, that would just, that you can use this to refactor it. Be interesting.
Okay, thank you very much.
The mentor is run already the rules?
Yes.
Yes, it's already, so I click on mentor.